Welcome everyone to this webinar, which is going to be a really interesting one that I've been looking forward to a lot myself. It's on seabed pipe sandy soil interaction, and it's going to be given by Joe Tom, who's an assistant professor at the University of Illinois at Urbana-Champaign. I think he will say a little bit more about his background shortly. As usual, if you have any questions, you are very welcome to type them into the Q&A field that opens if you press the Q&A button at the bottom of the screen. Today we have also decided that, or Joe has agreed to take actually questions, say verbal questions. So what you can do is you can raise your hand, and then we will put you online, as someone has already done. But if you raise your hand when we come to the Q&A session, if you want to ask a question in person, then raise your hand and we will unmute you. So I think that's it. And so over to you, Joe.
Thanks, Christian. Thanks everyone for showing up at the webinar. Good morning, I guess, for me, good afternoon for Christian, and good evening for some people, hopefully. As Christian mentioned, I'm at the University of Illinois at the moment. I've been here since January, so I just arrived in the US. Before that, I was at the University of Western Australia. So a lot of the work, well, all the work done here was done when I was back in Australia. So you'll see a lot of context for offshore Australia in terms of what we're going to talk about today. So yeah, the presentation is really about seabed pipe soil interaction. I threw in the word sandy there. Just because what we're really talking about is sand and kind of how that is a unique thing to model, and how we can incorporate OPTUM, well, how we have incorporated OPTUM into some of these kind of practice-driven research areas. So a bit of context for offshore pipelines. Primarily we're talking about oil and gas pipelines here. So the concepts that we're going to talk about are applicable to offshore renewable energy as well. But for the drivers of what started this research, we're talking about oil and gas pipelines. So that's flow lines connecting different subsea infrastructure and also exporting out to the processing facilities, as well as umbilicals. And that's sort of where the renewable energy comes in for renewable energy cables. From a geotechnical perspective, there's, I guess, broadly two design aspects that we're interested in. First one is on-bottom stability, or stability of pipelines in environmental conditions, and the second one would be high temperature, high pressure, or rather management of high temperature, high pressure global buckling issues. So stability, we're offshore, so there's currents, there's waves, there's tides that have some influence near the seabed. And if you have a pipeline that's sitting on the seabed, the question is, when those hydrodynamic conditions load the pipeline, do we have enough resistance provided by the seabed to keep it in place? So where we put the pipeline on day one, is it still going to be there at day 1000? That's the question for geotechnical engineers. Global buckling, so pipelines that have high pressure and also very hot oil and gas inside them, they warm up. And when steel or other metals warm up, they want to expand. Because of system constraints, they cannot necessarily expand axially, so forces build up in the pipeline. And in order to relieve those stresses in the pipeline, they have to move somewhere, and that's what's known as lateral buckling. So they move, instead of being in a straight line, they'll move out to the side, away from its original track. And so for the pipeline engineer, what they want to know from geotechnical engineers is, what is the soil resistance? And we need to be quite accurate with the prediction of that soil resistance, because they want to manage the buckles. So the buckles will occur, and they want to be able to predict when and where they will occur to manage the stresses that occur in the pipeline. So in both of these cases, the pipeline engineer will take a typical sort of structural model where the input from the geotechnical side will be a kind of spring. So that might be an elastic plastic spring where we've got a peak. Can you see my mouse there?
Yes.
Yep, you've got a peak capacity, and then that might be plastic, or you might have a trilinear spring where you have some softening. One of the big questions for the geotechnical engineer is, how do we predict that peak capacity? And that's really what we're going to talk about in the research topics today. So I'm going to do 3 talks, sort of 3 mini talks, because I wanted to give an overview of some of the work that I've been involved with. And I shouldn't, this isn't just my work. This is the work with a lot of people, colleagues. But the 3 ones that we're going to stay high level on are, the first one is looking at sort of generalized solutions for breakout resistance of pipelines on sand. And when we say breakout resistance, we're really talking about the bearing capacity and what is the maximum load that the pipeline can take before it moves. Second one is sort of stability of pipelines that are on mobile seabeds where sediment transport is occurring. And the third one is some interesting creative engineering to look at the uplift capacity of buried pipelines. So jump into the first one. On the left there, we've got a picture of just a pipeline on a seabed. You can sort of see the sort of coarse grains there. So it's a sandy seabed, a little bit of embedment. So maybe 20% embedment, 10% embedment. As I said before, what we need to do as geotechnical engineers predict what is the maximum, for instance, what is the maximum horizontal load that the pipeline can take before it wants to move. For sand, we really have 2 considerations that we were trying to get towards, and that's basically why we did this work, and you can have a look at the paper later on in the ASE if you're interested. But the main 2 considerations are non-associated flow. So we'll talk a bit more about that, but the idea is that the dilation angle or the sort of volume change is not equal to the friction angle. That's important for sand. And the second one is the idea of interaction of the vertical and horizontal components, so combined loading effects. Talk about both of those, and then that will lead us into the solutions that we came to. So just touch briefly, not too much detail on associated and non-associated flow. Associated flow is sort of what's implicit in limit analysis. And so the idea there is if you shear, say, a block with an interface, it wants to move upwards. The angle that it wants to move upwards at is the friction angle. And that's just the assumption that is required for the limit analysis theorems. For non-associated flow, that's such that the distance that that block, for instance, wants to move up is not the friction angle. So it might be a lower angle, the dilation angle, or if it's a critical state, it will be 0 and it will just be sliding along that interface. This is important because I guess as a general statement, we can think that for the same friction angle, the associated flow capacity is generally bigger than the non-associated flow capacity. So for sands, which are in general non-associated, if we use associated flow, we might over-predict the capacity and not have good, accurate predictions of what we can expect. So that means with the limit analysis, we're sort of limited because that is associated flow. There are some ways to account for that, sort of by, for instance, reducing the friction angle to account for the fact that the dilation angle is not equal to it. But at the end of the day, it's also good to just go into the full elastoplastic FEA, and that's where OPTUM comes in to the situation here. So here's some, just to kind of illustrate what I think are the differences, an easy way to sort of think about these differences. On the left there is the strain field for an associated flow case, or a pipe just pushing down into a sandy seabed. And on the right is the same result from OPTUM using the multiplier elastoplastic finite element method, but with a small, or actually a 0 dilation angle there. So you can see the mechanisms are quite different. So for associated flow, you have to do a lot more work to push that soil out of the way relative to that for the non-associated flow. Plus the strengths are different, but we get a case where the associated flow has a much larger capacity than the non-associated flow. So what we did in the research itself was go into OPTUM and focus on the multiplier elastoplastic module using a more Coulomb approach where we can specify the friction angle and the dilation angle, and we can calculate capacities based on that. So in terms of some of the results, looking here on the y-axis is the calculated vertical bearing capacity, and on the x-axis is vertical bearing capacity. On the y-axis is sort of wished in place embedment. So this is what is the capacity as you increase the embedment of the pipeline incrementally. The line there, the solid line, is the limit analysis for associated flow, and the dots are the FEA results for different values of friction or dilation angle, the same friction angle. So you can see as the dilation angle reduces, the capacity reduces for the same friction angle. So why is that important? It's kind of interesting to then compare the elastoplastic FEA results for non-associated flow with some experiments. So what we did in the paper is we compared versus some experiments done by Richard Sanford and Oxford a few years ago, where he had a bed of sand with a certain friction angle and density. we can associate the density using Bolton's relationships to give us peak friction angle and peak dilation angle. When we then compare the optimum results for the penetration resistance, in this case, the optimum results are the lines, not dots, so I sort of switched it there. So the dots are the experiments and the lines are the optimum results for different values of critical state friction angle. And you can see as we, somewhere between a critical state friction angle of 34 and 36, we bound the experimental results. So we have quite good comparison here with 1G experimental results and the predictions that come out of OPTUM. The question is, can we use this idea of a limit analysis? Because limit analysis is much faster than doing a full FEA calculation. It's sort of up maybe 5 to 10 times faster to do just simple limit analysis for the same conditions. So can we use that modified or reduced friction angle to account for the fact that the dilation angle is not equal to the friction angle? I'll go into the details of that, but this sort of idea was been around since the 60s and more so in the 90s with Drescher and de Tournay, where they said we can use an upper bound limit analysis with a reduced friction angle to give something close to the non-associated flow result. And if we compare then the dashed lines there with the FEA points, you can see that it gets us closer and we have the right trends, but it doesn't actually give us a good comparison for the vertical bearing capacity case. And it's, in fact, in some cases is about 50% lower than the FEA results, which again, as before, compared well with experiments. So set that aside for now, and then focus now on the second part, which is the interaction of vertical and horizontal load. So that's such that what we're saying is basically instead of a block sliding on a surface where it's just frictional, so there's a linear function, the horizontal load is a linear function of the vertical load. What we find is that the vertical load is the vertical load affects what the horizontal load value is. I guess before we get into that, there's these envelopes here that we can compare. The circles are the optimum results from the FEA non-associated flow for different values of dilation angle and friction angle. We've compared that versus Abacus results from Richard Sanford, where he used the same values, and we get very good response over the spectrum of a failure envelope. So you can see there's a nonlinear difference between, or a nonlinear effect of the vertical load on the horizontal load. So what we did, so we're reasonably confident that we can get good results out of OPTUM. So then you did a parametric study where we varied the critical state friction angle, the dilation angle, and the embedment to give sort of generalized failure envelopes. We can fit it with this analytical functional form where we have these four coefficients, I guess, that describe the overall shape of the envelope. And I sort of give relationships that are kind of first order in the paper. So you can reference that if you're interested in that. But I guess the main thing to point out is that that's all well and good for the overall shape of the failure envelopes. But for pipelines sitting on the seabed, what we're really concerned about is what's happening down near the origin. Because when you have a pipeline sitting on the seabed, it's been laid there, and the only vertical load is the self-weight of the pipeline, and that's nowhere near the vertical bearing capacity of a sandy seabed in general. So let's zoom in there and see what's going on in terms of the interaction. So here I've plotted on the x-axis applied vertical load, which is constant, and then values of the non-associated flow FEA results, where the horizontal capacity required to move the pipeline is normalized by that constant vertical load with different embedments for a given difference between the friction angle and dilation angle. Again, we see that nonlinear change in the so-called friction factor. But we see, so it's that value of H over V is often called a friction factor in offshore pipeline design, but you can clearly see it's not really friction. It's not really a frictional factor because it's changing with time. So it does, the value of this ratio depends very strongly on the value of the applied vertical load. But then maybe in this case, because again, those elastoplastic analyses can take quite a long time, 10 to 20 minutes per run. So there is some advantage to potentially going back to that idea of limit analysis with a reduced friction angle to account for these differences in the dilation angle. And we can see if that gives us a reasonable estimation at this stage. Obviously, I'm leading the witness here because it does. So those lines there represent the upper bound limit analysis where we've now used this this equation to reduce the friction angle that we input into OPTUM. And we then calculate the friction factor there. And we can see we get a very good comparison between the two. And the reason why that is when you're looking at primarily horizontal loads with relatively low vertical loads, the failure mechanisms between the non-associated flow and associated flow are pretty similar. So the associated flow there, the dashed lines, and the solid lines there is the failure mechanism for non-associated flow, and they're pretty close, hence the work done for these things are pretty similar as well. Whereas for the vertical loads, that wasn't really the case. You had a much bigger mechanism and a lot of different things are going on there. So the advantage, as I said, is sort of much faster to do a limit analysis. And this is a really good thing for industry because it means we don't necessarily need to go to the full FEA calculation to get failure envelopes if we want it. We can do limit analysis as long as we focus on the relatively small values of vertical load. So we can still use an upper bound limit analysis to do that. I guess that's just as a practical aside, since it's an OPTUM webinar, I thought I should mention that how I did all those dots there with the elastoplastic analysis is really good using the batch processing feature in OPTUM. So basically, if you set up your geometries and profiles, you can just have a simple MATLAB code or MATLAB or Python code that writes a batch file. And then in the background, you run that batch file through MATLAB or Python, and the OPTUM will run in the background. So instead of having to just wait and stay at the GUI for 10 minutes for your thing to run, you can just set it up overnight, run it, and then hopefully it's done in the morning. So that's one of the nice features of OPTUM that allows you to do lots of these multiple runs very quickly. So just to summarize this first bit, again, a shameless plug for the paper, so go out and have a look at that in ASCE. I think the main thing to point out was that we did the non-associated flow, the full FEA in OPTUM, which worked well, compared well with experiments and previous numerical results from Abacus. But it takes a long time. So what we wanted to do was try to use the limit analysis associated flow, reducing the friction angle. And that worked well for breakout condition of operational values of pipe vertical load, so low values of vertical load. But it doesn't really work well for the vertical bearing capacity for calculating embedment. And so those are the sort of main takeaways, but this underline here is really good for industry because it means we can do the simpler calculations and give us positive results. So let's build on that a bit and think about how we can then do those sorts of calculations to explore the stability of pipelines on mobile seabeds. So when I say mobile seabeds, as I mentioned before, mobile seabed is one that is sediment. The sediment is actively being transported due to the environmental conditions. And so that means that the geometry is changing. And so instead of having a relatively flat seabed, we have different types of seabed, which are unique depending on the mechanism that's occurring. So I should, the context of this are operating pipelines in the Northwest Shelf of Australia. And a lot of the background to this is due to this gentleman down here, Simon Leckie, who was doing his PhD at UWA, is now in Cardno in Perth. And basically what he did in his PhD was he looked at surveys of a couple of pipelines in the Northwest Shelf and observed what their embedment condition was like right after pipe lay or right after installation, and then later on down the operational timeline. But this is one example for a pipeline. This is about 6 months after the pipe lay. See, it's a relatively flat seabed, a little bit of deposition to the sides, but not much. But then when he went back and looked, and I should say these are just 3D representations of his bathymetry scans. And then when he went back to look 4 years after installation, he found the pipeline itself, as you can tell by the red here, has lowered relative to the ambient seabed level. And you also have a lot of areas of either spans or very deep local embedment of the pipeline. So the local geometry of the pipeline is changing, and the amount of soil next to the pipeline is also changing due to these effects. Very high level is a big field of sediment transport and scour around subsea infrastructure, but just to give you an idea, what we're talking about is hydrodynamic loading around pipes. So that's currents, particularly in the Northwest Shelf. We're talking about tidal currents, the occasional waves due to cyclones, but also primarily internal waves of solitons, which are driving the sediment transport. There's a couple of mechanisms that can cause geometry changes. The first one is piping. So you have piping beneath the pipeline leading to tunnel scour, so removal of the sediment at a location beneath the pipeline. So there's a hole now beneath the pipeline. That hole can grow along the pipeline, or can occur at multiple places along a pipeline. And either of those leads to various mechanisms of the pipe lowering relative to the ambient seabed level. And you can get varying scenarios of a pipe sitting in a trench where you have a little bit of embedment, but instead of a flat seabed moving up, we now have a sloping seabed moving away from that local embedment position. And we also have locations such as at span shoulders where we have very deep embedment, almost up to fully buried pipelines. Whereas when we first laid the pipeline, it only had about 10% of embedment, and now we've moved to about 90% of embedment. Big changes in the embedment condition. Just to mention briefly, there's also the another mechanism potential, either due to leewake scour or sort of ambient sediment transport, where you get local deposition. So you get formation of these sort of triangular berms on the sides of the pipeline. So this work was sort of started back in 2015. And here we used OPTUM for limit analysis. So we took advantage of the previous section, the talk that we showed, where at operational conditions, limit analysis works well as long as we know the idea about the friction angle and the dilation angle and what it should be. Then we went into, Simon and I had a look at his data for a particular pipeline section and statistically looked at the cross sections of the seabed profile at positions along the pipeline. And so this is a case in 2002, which is basically right after pipe lay. So if you focus on the blue line there where my mouse is, that is sort of the P50 or the median profile for that particular, I think, 200-meter long section of pipeline. So you have about 40% embedment, but then you have a gentle downward sloping seabed going away. So you have a bit of deposition there. Then if we look 4 years later, that median profile is now about 70 to 80% embedded. And instead of a downward sloping seabed, we have either a flat or upward sloping seabed. So thinking about what that means in terms of the amount of soil that needs to be pushed out of the way to push the soil sideways, there's a lot more soil in this case. You know, it doesn't seem to be much of a difference in the embedment profile, but actually it makes a big difference. And when we look at the changes in the horizontal capacity for different values of vertical load for those two profiles, we see that we get almost a doubling in the horizontal resistance, simply due to the changes in geometry that resulted from sediment transport over that time period. A bit of later work that we published last year tried to do a bit more kind of generalized equations where we can, if we know the value, if we know the value for a flat seabed, we can then modify that to consider the seabed slope and the local embedment. And that gives us a fast way to do calculations for the local resistance on the fly. And I guess one implication of that is some work that Simon did where he took similar sort of, excuse me, relationships. He looked at a particular pipeline. So here we're now looking at a 200-meter long section of a pipeline in terms of the local embedment. So the as-laid embedment was about 0.2%, sorry, 20% of the diameter, which corresponds to an as-laid capacity of 0.2 kilonewtons per meter, roughly. So just a little bit of resistance to resist the hydrodynamic loading. But what happens when we see these observed sediment transport induced embedment changes over time? What he found was over that 200-meter section, you have parts of it which are in span, so it's completely lost the embedment. So in this part, there's no soil touching the pipeline. And then in parts next door, you have lots of embedment. So you've gone from 20%, say, up to almost 100% in locations, so almost fully buried pipeline there. And it's sort of this hill and trough kind of, or hill and valley sort of behavior that we see. When we plug those into equations like this and limit analysis type calculations, what we see is areas that are in span, they of course lose all the capacity. But just next door where we have lots of increase in embedment and changes in the seabed slope, we get a lot more capacity locally out of the system. So then the question is, even though we have a lot of places where there's spans, when we look spatially averaged over a pipeline length, have we increased or reduced the stability in practice? And so Simon's paper, which is in ocean engineering, basically what he found was when you look at it over the length for this particular pipeline, the changes in embedment led to an increased stability of about 1.7, so 70% increase in stability, almost doubling of the overall stability of the pipeline. So what that means in practice is potentially if we could account for these changes, if we could predict them and reliably bank them, that could lead us to reducing the SG of the pipeline. So we could make the pipeline lighter. That would be less concrete weight coat on the outside of the pipeline, and the concrete weight coat is put there to increase the stability. So we maybe don't need that concrete weight coat as much anymore. So talked about sediment transport induced embedment changes and how we can use limit analysis to predict the resistance effects of that, and showed the particularly the results of that on the stability of a particular pipeline on the northwest shelf of Australia. I guess quite a few caveats in there is that that was for a particular pipeline which had a certain sediment transport behavior, and certain mechanisms were occurring. The scour and lowering did occur there, and hence the stability did go up. It doesn't necessarily, that doesn't mean if you don't go to a place that has a different type of sediment or it has a different mid-ocean conditions, different mechanisms will prevail, and you may not get these increased embedments and stability. So we have to know or predict how quickly and what type of profiles will evolve after installation if we want to be able to account for this in design. And this is really where a probabilistic framework kind of fits in. So thinking about the soil properties probabilistically, but even more important is the mid-ocean conditions and the environmental conditions, thinking about that probabilistically. And some of this stuff is work that was done in the stable pipe JIP, and you can read some of those papers in OMAE from a couple of years ago. So yes, so the last one here is some work we did looking at the uplift capacity of buried pipelines, and then some, I suppose, bit creative engineering to see if we can't increase the capacity of those pipelines. So I guess just to start off, I'll just should acknowledge my the people who helped out with this. So Technique FMC in Aberdeen, that's Ali and Alistair. They funded the original experiments that were going into this work, and then we brought in OPTUM afterwards to sort of expand the research, which we then were able to publish a couple of years ago in Geotechnique Letters. But so a buried pipeline, what the idea here is we have the seabed. Instead of laying the pipeline just flat on the seabed, what we do is we dig a trench and we lay the pipeline in the trench and then backfill the pipeline and put soil back on top of the pipeline. So if that pipeline is a high temperature, high pressure pipeline, it still wants to expand and still has the risk of buckling. In this case, instead of lateral buckling, it has upheaval buckling. So it wants to move upwards out of the soil. I pulled this picture from Google. I don't know that that pipeline is actually upheaval buckling, but it sort of illustrates the point of what could happen if you don't have enough resistance when it wants to buckle. It sort of pops out of the ground. And it could, of course, lead to overstressing of the pipe. I should say why they bury it is in general for protection. So in places like the North Sea on the east coast of the US, you have a lot of ships which have anchors, and you don't want the anchors to run and snag the pipeline if it's sitting on the seabed. And other things like fishing that have bottom trawling, you don't want that fishing gear to snag the pipeline. And other, even more interesting in Newfoundland and in Canada, they bury the pipeline to prevent icebergs from smashing into the pipeline. So lots of reasons why you might bury the pipeline. And so what we want to do as geotechnical engineers is predict the peak uplift resistance. So how much resistance does the soil cover provide from the pipeline moving up? And then the pipeline engineer can use that to design their system. So if we don't have enough resistance, what are the options? So one is bury it deeper. So we need to dig a bigger trench, which means we need to have a different set of equipment perhaps, which is more expensive. The other idea is a larger diameter, which has other implications for flow assurance and that sort of thing. So that may not be a suitable approach. So the question posed by Technique was, can we improve the resistance by adding attachments to the pipe? So can we add external hinges to the pipeline to change the footprint and therefore increase the amount of soil that has to be sheared in order to fail the soil? So you can go from just a regular pipe with no fins over to different sorts of geometries with little fins or strakes sticking out at different orientations, so in different lengths. So just a little illustration there. These tests were done back at the beginning of my PhD at UWA at the National Geosectoral Centrifuge facility there. So we did it 1G, where we buried the pipeline, put sand in there and then pulled it up. We were able to do, it's in loose sand, and we were able to do PIV measurements to visualize the displacement field, but also measuring the load to see how the load and the capacity changes for these different geometries and orientations. So some of the results there on the left for three of the pipe types, where on the x-axis you've got the uplift force, so how much force is acting on the pipe versus different levels of displacement. The black line there is the plain pipe. The blue line there is the pipe with the center strake pointing up, and you have the two lateral fins at the bottom. And the yellow line is where the lateral fins are at the top. So just flipped it 180 degrees there. And what we generally see is we have a peak, which reduces as we move the pipe up through the soil towards the surface, which is as expected. And then what we can do is look at the value of the peak resistance here measured and see how that compares for different pipe types. So when we look at the case where the lateral fins are pointed down, we in fact see an increase. So we see somewhere, and I guess I should say the variation here is to do with the variation in embedment. And so anyways, we see an increase, which is a function of the extent, so the length of those fins, as well as the orientation of the fins. So when we have them oriented at the bottom, we get an increase up to about 25% of the regular pipe capacity. But when we flip the whole thing upside down, we actually see reductions in the capacity, small reductions, or at best a marginal increase. So there is an increase that in general, we can increase the resistance of buried objects by attaching things or having geometry changes, I suppose, of the object, but it does depend very much on the geometry of the object itself and the attachments that you make. So second part is that we went in, did some OPTUM. Let's see how we go. We go into limit analysis first, upper bound analysis. We have our pipe put in there, we pull it up, and then we measure the resistance on the pipe, and then compare that to the model experiments. What we see is when we compare to the model experiments for limit analysis, which again is associated flow, we get an over prediction of the experiments by about 50% when we use the same friction angle. And the reason for that is because you can see the mechanism here is basically a big triangle of soil which is being lifted, and the angle between the failure plane there and the vertical is about the angle of friction there. So that's quite a big volume of soil that has to fail in order to pull the thing out. We did mention the idea of reducing that friction angle to account for the dilation angle. When we do that, we still overpredict the experiments by about 30%. So it's not, for this particular boundary value problem, limit analysis is not really that appropriate. And this sort of thing has been pointed out by many people before, including Christian. And I should say it's not appropriate for sandy, non-associated materials. So for clays, undrained materials, it's perfectly fine. But for sands, then we need to think a bit more about it. What we can do is kind of take an analytical approach. This was some, estimation done by Dave White and Johnny Chuck 12 years ago or so, where they looked at the uplift resistance of a pipeline, buried pipeline using limit equilibrium. So here we can specifically define the failure geometry, and we can define that, that angle as corresponding to the dilation angle of the soil. We have to make some assumption on the stress conditions acting on that failure plane. And then when we compare that limit equilibrium method to the experiments, we see a much closer estimation than the limit analysis. This time we underestimate it, but that just depends on the conditions and the assumptions that we make. But all is not lost for OPTUM. So we went back into our OPTUM, go back into the finite element elastoplastic module. We then plug in the correct value of friction angle and dilation angle. And what we see in terms of the failure mechanism, or the refined failure mechanism, is we have now an angle that is approximately equal to the dilation angle. So we're lifting much less soil up now in this case. And when we compare versus the experiments for this pipe, we get within 1%. Obviously, it's not always going to be within 1%, but for this condition and for these scenarios, it worked out quite well. So that's very promising. We were able to do the same sort of things for deriving a limit equilibrium equation for if you have fins on the pipeline and you do have a shallow failure mechanism. And we went in and plugged into OPTUM with the FEA with the appropriate friction and dilation angles, get some results, and then we can see that the trends are very good for both of the cases. So our numerical results are bounding the experimental results over the range of embedments for the fins down configuration, and the limit equilibrium is doing as well. And then for the fins up, in both cases, limit equilibrium and the optimum results, we see a reduction, or at best a limited increase in capacity, which is exactly what we saw in the experiments. So what this means basically is that if you want to do something where you're changing the geometry of a buried structure and wanting to look at how that's affecting the capacity, limit equilibrium, if you can derive a limit equilibrium for that, for the particular mechanism, or you can use OPTUM, but specifically the multiplier elastoplastic module, not necessarily the limit analysis module, that can give you good comparison to the experimental results and can be used in sense for design. So we talk a bit more about different things in the paper. So here's just a bit of a peek of comparing the optimum results there for the finite elements on the left. So that's sort of contours of displacement field during peak uplift versus the PIV experimental results. And you see for certain conditions, we can get good comparison between what's happening in the experiments and what we observe in optimum. So that's a very promising sort of thing. So I think that is pretty good on the time. So that was just a couple of the different areas that I've been working in terms of seabed pipe soil interaction and how we've incorporated OPTUM into that work. Thank the audience, but also like to acknowledge my colleagues and co-authors in this. So Dave White, University of Southampton, Scott Draper's at UWA, Simon, who's was at UWA now in Cardno, Terry Griffiths in UWA, as well as Coneth O'Loughlin, and then Alia Gai, formerly of Technique, and Alistair McConaughey from Technique. So thanks for your attention and happy to answer any questions.
Thanks a lot, Joe. That was extremely interesting. Very nice presentation. I have a couple of questions myself, but I think we'll see what the audience says first. And as I said at the beginning of the talk, if any of you want to raise your hand and ask a question live personally, then you're more than welcome to do so. So we might take them in order, Joe, the questions that are there, and again, if you have any questions, it's the Q&A button at the bottom of the screen. So there's a question: what about soft silt or clay? So this was for sandy soils, and you mentioned there was some particular challenges when it comes to sands. So I don't know if.
So yeah, for soft silts and clays, that is a lot more work has been done. Say a lot more work has been done, and it's much more tractable from an analytical perspective. I think I've got another slide here. So this plot up here at the top is comparing limit analysis from Martin and White from a few years ago, and that's pretty similar to what is basically used as the industry standard for clays that behave in an undrained fashion when they break out. And then I've compared on top, the dots there are OPTUM limit analysis results. So OPTUM for limit analysis works perfectly fine for clay and is consistent with the typical industry standard work. So with clay, you don't need to worry about the non-associated flow as such as much because it's undrained, and so the dilation angle is zero in a sense.
And then for sands, this is another question. The friction angle might not be constant, right? It could depend on, I mean, these are all plane strain analysis, so it's kind of the plane strain angle, I guess that's the appropriate one, but it could still be stress level dependent. Is that something that is something you have considered, or it's not relevant? You're outside the range of the confining stresses where the dependency is greatest. So of course, at very low confining stresses, you can have quite a bit of variation.
Yep.
Quite variable.
I think there's two questions there. One is about stress level dependency. It's very important. And so if I jump back, there's two sort of things that are useful to point out. If we have a look at the center figure here, so we've compared versus some experiments. This is again going back to the vertical bearing capacity. The experiments had a measured relative density, and we know the friction angle of the soil. So we can then link that to what the friction and dilation angle should be for that condition. So if you had a different density, you would get a different friction angle. So you need a way to understand the density and also understand what that means for the friction and dilation angle. In general, I have been using Bolton's equation. There's other sort of approaches you can use to consider that stress level effect. But basically, when you go into the FEA, you just need to plug in the correct value of friction angle and dilation angle. The second, I was actually showing the wrong screen there. The second aspect is, you know, as you displace, you also might change or as you shear something, there's sort of strain-induced changes in the friction angle. So you get towards a critical state friction angle. And so your dilation is essentially changing during the process. This won't account for that. So what we've done here is specified the peak, what we think is considered the peak friction and dilation angles for the conditions. And so essentially what we're getting out is just this point. We're just getting out the single point of the peak resistance. So it's what is the peak dilation, what is the peak friction angle, therefore what is the peak resistance of our system.
Sure, great. Just one comment on that. In OPTUM, there's a model called GSK, which is kind of a nonlinear Moore-Coulomb envelope. And there's the Bolton model as well, from Bolton's paper, the 1986 paper, I believe. But the GSK model is, so it's similar, and it's kind of what I think matches experimental data a little bit better than Bolton. And what we've done as well is calibrate this model to a large database of sands from NGI, so that you are actually able to enter a relative density and then internally a stress level dependent friction angle will be calculated automatically. All the equations and everything is in the manual. So that might be something to consider.
Yeah.
How much variation would you expect between the Western Australian results and the kind of so that's sort of calcareous sands and the U.S. Gulf? It says, I guess it's the Gulf of Mexico type materials.
So I guess that Gulf Coast sand, but I think the main thing we should consider there is maybe more so in the crushability and the compressibility of the carbonate sands. So in terms of especially the displacements, I think, which we haven't really talked about here, you would expect potentially having a condition where you start to get crushing of the carbonate sands, which you're unlikely to get in the silica sands. And so that would probably affect things. And just in general, we see a lot of higher friction angles in the carbonate sediments as compared to, I suppose, more traditional silica sands. And so that would need to be incorporated in terms of the values of the friction angle that you use, friction angle, critical state, and peak friction angles that you use. Those are the sort of two things that come off the top of my head.
Sure. Then on Davis, you had some really nice examples of the application of the Davis correction there. And I think it's fair to say that sometimes it's spot on. Sometimes it underestimates the results, the capacities that you find with a full non-associated analysis with the initial vertical capacity examples that you showed. And sometimes it underestimates the capacities. So for the deeply buried, the last set of examples you showed.
Right.
So It's not conservative and it's not unconservative. It's really problem dependent, but it of course does always lead to a reduction in capacity compared to what you would find with a non-associated with an associated analysis. Um, so and I would say, I don't know if that's your experience, but I would say that for sort of shallow problems like this one that you're showing there, the Davis approach tends to underestimate the capacity, and for more highly confined problems, that there is a tendency that it'll underestimate it.
Yeah, yeah. Oh, overestimate for the more confined problems. Yeah.
Yeah, sorry, overestimate, yeah, and underestimate for these shallow problems, yeah.
Yeah, that's pretty much it. I mean, if you, yeah, as you say, it's not. I mean, the good thing about if you are doing limit analysis is that it is rigorous, right? So you can get an upper and lower bound, and you have a solution for the mass. But the Davis, in a sense, doesn't give you anything rigorous like that. It's in a sense of an estimate of what the capacity should be.
I would say though, Joe, that you, in this particular example, I thought you were a bit hard on the Davis approach. I mean, I know it does underestimate it quite a bit, but did this example or the capacity here would be pretty sensitive to the friction angle as well, right? So,
yeah, I guess it's you know, and in a sense for sands, this is, I suppose, less important than the operational conditions here at low vertical load, where the Davis approach works actually quite well, very well, in fact. So, yeah, yeah, okay, that's a bit harsh there, but it does give you the right sort of trends, and it gives you the right, you know, orders of things.
Sure.
Indeed.
And as you show as well, I mean, I think where the main difference, if that's of importance, is the failure mechanism, which are really very different in the two cases, right? I mean, they're really, really different. You have much more soil activated in the associated case than in the non-associated case.
Yeah.
That one there.
Correct, yeah. And that was also seen in the uplift case, which is, you know, if it is associated, you just have to lift more soil out. And that's a more direct, I think, comparison of the sort of issues with taking a Davis case. But yeah.
Then I have a question on the fins. I know your paper there from Geotechnique Letters, which it's really interesting, the effects of these fins. Is that something you've considered with respect to the horizontal capacity, the effect of those fins and the orientation of them and that kind of thing?
I guess the answer is no, we haven't considered that. In this case, we just looked at uplift capacity. It could be an interesting thing to do that. I suppose it all comes down really to, you know, the structural design of the fin. Is it going to be robust? Because that's a sort of small piece of thing that's sticking out. So that needs to be carefully designed. And it's also about manufacturing tolerance, in terms of, because we did see that, you know, if you put it in the wrong direction, it doesn't quite work out as well. So that is maybe sort of an issue with general implementation. They do have, you know, these sorts of fin type things are used on pipelines, but mainly for a different purpose, for pipelines in the water to prevent vortex-induced vibrations. So there is a history of attaching these sorts of things, just not for the purpose of enhancing the geotechnical resistance. But it's definitely something that could be interesting.
Yeah. And also, in one of the first slides you showed, you had a picture of a pipeline on the seabed, and I was going to ask, yeah, maybe a slide 6.
6. Oh yeah.
And that reminded me of what is the roughness of these pipelines, and this seems to look pretty rough.
Yeah, extremely rough. I'm not sure how that affects the geotechnical properties, except in the case where the sediment transport buries the pipeline, because underneath you can't really, I mean,
Okay.
if it's embedded the whole time, it can't grow anything there, right? But for the burial case, that could be an issue. The other sort of thing is, which was pointed out in the paper by Simon there, is, you know, there's issues with roughness. There's also issues, which isn't geotechnical, but if you get the sediment transport changes and you get spans forming, that actually reduces the load, or can reduce the load on the pipeline. So I only talked about the geotechnical part of this, but these sediment transport changes are quite complex, and the interactions with the overall pipeline design are quite interesting there.
Yeah. Yeah, just back to the fins problem there. I had another question on that. I thought, or maybe not. Yeah. If you go back to the uplift with the fins, where you have the experiments versus the OPTUM results, you had the deformations. I think you showed. Yeah, the 27. So yeah, that one, numerical versus experimental. So there's pretty good sort of agreement, you could say, but it's as if the experimental one, it doesn't come all the way to the surface, the failure mechanism. Is that right? It's a
that
kind
is
of
right.
failure there.
Yeah, so it's a very interesting conundrum, and basically what we saw is because it's loose sand, we get like a area of compression of the sand above it, and it's a sort of, in a sense, a localized mechanism. So it doesn't extend all the way to the surface. And these sorts of things have been observed for loose sands for other people. And so part of what is the discussion in the paper is actually that if we use the right dilation angle, we get the right capacity, more or less, in OPTUM, but we don't quite get the same sort of mechanism. So the mechanism is different, and the same thing for the limit equilibrium. So there's something interesting happening where we do the same amount of work for a different sort of mechanism than was actually observed in the experiments. Now these results here that's where I sort of tweaked I reduced the dilation angle until it starts to be sort of compressive instead of expansive or dilative. And that reduces the capacity a bit, but it actually only reduced it about, I think it was about 10 to 15%. So it got us much closer for visualization purposes to the mechanism. And it didn't do too much to the predictions in terms of the capacity. And I mean, I think that's what we broadly think is happening here, is it's densifying because it's loose. You really have what is essentially a negative dilation angle occurring there. So it wants to come together when it shears.
Yeah. Okay, really interesting. There's a final question in the Q&A box there, Joe, about the global stability number for pipelines. Maybe you want to comment on that?
Yeah, so the question is that we presented here on how the stability in this particular case goes up as a result of the sediment transport. And then the question is sort of about global buckling, which I conveniently didn't mention here in this part. And that is a very good question, and is agree with the poser, is that if you have all these large areas of span, that's a potential risk for road buckling and that sort of thing. And so I think there's a lot of people, or some people working, at least in the industry, at least in Perth, at how do we consider sediment transport in the context of buckling, which is a more complex problem, I'd say, than stability. Because in a sense, stability going up is always good. If you get more capacity, you're more stable. But for buckling, going up is not necessarily good, because that changes where the buckles occur, which makes the reliability of the buckle, the overall system, pipeline system, potentially worse. So agree, something we've thought about, something I've thought about, but haven't actually pursued yet about how to take that into context. I mean, I think one way is a sort of, one way that it's done is a probabilistic approach. So you probabilistically have to assess, moving along the pipeline, what is the condition of the pipeline going to look like, and what does that mean in terms of the buckling characteristics of that pipeline.
Cool. And maybe the very last one, that's to do with the interface condition. So I'm assuming you've used the just the standard OPTUM interfaces with so it's frictional contact, and you have the possibility of specifying a roughness. So I don't think you can do it in many other ways. You can of course play with that roughness, but there is some friction at that interface. I think that's the way it is.
In the results, we used rough as a general, and you know, if you, most of these pipelines are concreted, are coated with concrete, so they're pretty rough in general. So I think a rough assumption is reasonable. You could use a smaller one. We did some work using a smooth interface, but the results presented are for rough interface.
Yeah. And very last comment, and that has to do with the batch computations that you really showed a really nice example of. It's something I use all the time myself, but I don't think it's that widely used. There is actually a manual that comes with the program that describes how to do that. But the idea is, as you outlined, Joe, that you set up your OPTUM files, your G2X files, with the interface, of course, and then you run them outside of the interface. So you call the computational engine without actually activating the graphical user interface. There are various other ways of doing that on our YouTube channel. There's a video on not exactly batch runs, but how to basically call the computational core through MATLAB. That is in that case, but it could be done through Python as well, without using the user interface. So for these kinds of runs, for these kinds of analysis that you've shown here today, I think that's the way to go. Yeah. Probably, yeah. But there is a manual that comes with the program that describes all of that as well. Okay, so thanks again, Joe. It's been a really interesting presentation. Thanks everyone for showing up, and thanks for your questions as well. So I think we'll end it here, and but if you just stay on the line, Joe, we'll just have a short chat.
Yep, no problem. Thanks.
Bye-bye.